Dear children, today we will discuss temperature dependence of resistivity. So now that means suppose you have a conductor, you know the resistivity doesn't depend upon the shape and size of a conductor. It doesn't depend upon the length and area of cross section of a conductor. But resistance that depends upon the shape and size of the conductor. So now, how resistivity and the resistance depends upon temperature. So let us come to the topic. Temperature dependence of resistivity. Here it is rho T is equal rho 0 whole into 1 plus alpha T minus T0. Alpha is called as temperature coefficient of resistivity. Rho 0 resistivity of the material at temperature T0. Rho T is the resistivity of the material at temperature T. So from this expression you can write now alpha is equal to rho T minus rho 0 divided by rho 0 into T minus T0. That means this temperature coefficient of resistivity is the change in resistivity per unit original resistivity per degree rise of temperature. Similarly, resistance that also depends upon temperature, the similar formula in place of rho you can write R. RT is equal to R0 whole into 1 plus alpha T minus T0. Similarly, alpha that equal to RT minus R0 by R0 into T minus T0. So here question arises, this alpha is called as temperature coefficient of resistance. So what is the unit of alpha? Alpha you need to remember, it is change in resistivity per unit original resistivity. Resistivity unit cancel. That is alpha unit will be 1 by temperature unit. Temperature unit, SI unit you know Kelvin. So SI unit will be Kelvin inverse. SI unit of alpha, that is Kelvin inverse, and CGS, that is degree Celsius inverse. So now we will discuss why this resistance or the resistivity depends upon temperature. So to understand this, first you know why a conductor offers resistance to the flow of current through it. So you remember, suppose you are asked to go along a crowded road. So when you go along a crowded road, definitely your speed will be less because you have to pass through a number of people. There may be collision with the other people. So, if you are asked to go along a free road, free plain road, then you will not get any collision. You will not get any obstruction. So, your speed will be more. But similarly, in case of conductor, you know conductor consists of large number of free electrons. When you apply potential difference, then the electrons will go from lower potential to higher potential. When the electrons will go from lower potential to higher potential, it will get a number of collisions. And due to collisions, it gets opposition. So you remember, in case of conductor, the resistance is due to the collisions. More is the number of collisions, more is the resistance. So let us write the expression of resistivity, you know the resistivity rho is equal to m by n square tau. So you see, here I will write rho is equal to m by n square tau, or resistance is equal to ml by na square tau. So you see, for this expression, this n is mass of electron and n is number density of free electrons, and E is charge of electron and tau is the relaxation time. For a conductor, this mass of electron and charge of electron is constant. So when you increase temperature, definitely n is the number density of free electrons. When you increase the temperature, then some other electrons will become free, so n will increase. When T increases, means temperature increases, n increases. Then what happens to the relaxation time? The relaxation time is the time in between two consecutive collisions. So when temperature increases, then kinetic energy of the free electrons increases. As kinetic energy increases, then the electrons collide more frequently. That means the relaxation time decreases. The time interval between the two collisions decreases. Then tau decreases. So from this explanation, you can know that the change in temperature has the effect on N and tau, as resistivity and the resistance depends upon N and tau, so resistance and the resistivity depends upon temperature. So now we will discuss how the resistivity changes in case of metals, in semiconductors, in insulators. In metals, what happens? In metals, what happens? A metal has large number of free electrons even at low temperature. So when you increase temperature, some electrons become free, but that increase in electron has very less effect on the resistivity. But if you increase temperature, then the relaxation time decreases. The electrons collide more frequently, and this collision increases. And this collision, or you can say it is the relaxation time. You remember, the relaxation time depends upon temperature only. As increase in temperature causes decrease in relaxation time, and here the decrease in relaxation time or decrease in tau dominates increase in N. So rho, as tau decreases, so rho increases. When temperature increases for metals, rho increases due to decrease in tau. Repeating again, here also N increases, but the decrease in tau dominates increase in N. So the resistivity increases in case of metals. But in case of semiconductors or insulators, what happens? You know, in case of semiconductor and insulators, there are very less number of free electrons. So when you increase temperature, then some more electrons become free. So here, and as there is very less number of free electrons, so meaning of relaxation time here the relaxation time has no effect on the resistivity. Here N has more effect on the resistivity. As here N, when temperature increases, then N increases, and this increase in N has more effect on the rho than decrease in tau. So resistivity decreases. So you remember, for semiconductor or insulator, the resistivity decreases with increase in temperature. But in case of conductor or the metal, the resistivity increases with increase in temperature. So you see here, as here resistivity increases with increase in temperature, here rho T more than rho 0 for metals. So alpha is positive, as rho T more than rho 0. But in case of semiconductor or insulator, the resistivity decreases with increase in temperature. So rho T is less than rho 0. So alpha is negative. So temperature coefficient of resistivity is negative for semiconductor or insulators. So now these are the graphs. It is for copper or metal. You see the resistivity versus temperature. The graph will be like this. It is non-linear. It is parabolic. And you see the graph starts from here, not from here, because the copper has some resistivity even at 0 temperature. Similarly for nichrome, you see the graph is like this, and the graph starts from here, because the resistivity is not 0 even at 0 temperature. And for semiconductor, the graph is like this. So you see here, for metal or copper, and for alloys like nichrome, you see resistivity increases with increase in temperature. And for semiconductor, you see the resistivity decreases with increase in temperature. So now limitations of Ohm's law. Limitations of Ohm's law. You know, for Ohm's law, temperature should remain constant. First one, temperature should remain constant. Remain constant. Second one, you remember, you know, metallic conductors, they obey Ohm's law. That means the graph between V versus I, that is straight line. But you remember, you take I along x-axis, V along y-axis, the graph will be straight line. But you remember, when high value of the current goes through the metallic conductor, then the current has the heating effect, and due to heating effect, the temperature increases. And as temperature increases, then no longer the conductor or the metal obey Ohm's law, because Ohm's law is valid only for constant temperature. So for high value of the current, Ohm's law doesn't obey. The graph will be like this. So you remember, Ohm's law doesn't obey for high value of current through metals. So now come to number 3. It also not valid for junction diodes. So junction diode, what is junction diode? You will learn the last chapter, chapter number 14. But now you remember Ohm's law doesn't valid for junction diodes. If you draw the graph between V versus I, the graph will be like this. It is not linear. So Ohm's law is not valid for junction diodes. So another one, it also not valid for gallium arsenide. For gallium arsenide, you remember the graph will be like this. You take it is current, it is voltage. The graph will be like this. It is, you see, initially the graph is straight, that is linear, but it is non-linear region, and you see in this region what happens, the current decreases even if increase in voltage. So what will be the resistance? Resistance is your del V by del I. As V increases, so del V is positive, and as I decreases, so del I is negative. So positive by negative, that is negative. So you remember, it is your negative resistance region. You see from the graph that the current, you will get same current even if at different values of voltage. You will get same, suppose you take this value of the current at different values of voltage. But this type of behavior will not find in case of metals or metallic conductors. It is so. What is your conclusion? Here also Ohm's law doesn't valid in case of gallium arsenide, GaAs. So now come to types of resistors. So you remember, for our domestic use or in laboratory, we are using two types of resistors. One is your wire bound resistor, number two carbon resistors. Wire bound resistor we are getting by winding wires of high resistivity. We are using the alloys like nichrome, manganese, constantan for wire bound resistor. So you can take one example of wire bound resistor, that is your rheostat we are using in the laboratory. So it is obtained by winding wires of alloys on a cylindrical core, and this wire bound resistor has very small value. It has the value of a fraction of ohm to a few hundred ohm. This size is large. But now come to carbon resistor. So to get high value of resistance, we will use carbon. By using carbon, we can get resistance of higher value. It is very small in size. So on a small size, you may have seen the carbon resistors we are using electronic circuits. Its size is very small. So to write the resistance value, on this small resistor we have to use color code. So now come to color code of carbon resistors. Color code of carbon resistors. So you have to remember one sequence. B. Roy of Great Britain has very good wife. So you remember B for black, this B is your brown, this R is your red, orange, yellow, green, and this B is blue. You remember there are three B's. First one is black, then brown, then blue. You have here two G's. One is your green, then is your gray. V for violet, then gray, then white, not white. So you assign the digits, and you know to write a number, you should use, you have 10 digits. So now you see there are 10 colors. So now you assign the digits. For black is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And also there are another two colors which gives the value of tolerance. Gold, it is 5%, and silver, it is 10%, and no color, it is 20%. So how do we get the resistance value from the color coding? Suppose you have a carbon resistor. So you have here a band of colors, band of 3 colors or 4 colors. You remember the fourth color gives you the tolerance value. Let us take one example. Suppose it is red, it is orange, and it is green, and it is gold. So how can you know the resistance value? You see, first color is, it is a band of 4 colors. There may be 3 colors because the third one or the fourth one gives you the tolerance value. If there is no fourth color, then the tolerance is 20%. So for red you see it is 2, assigned digit is 2, and for orange you see it is 3, and you remember the third color gives you the multiplier. The third color is your green. You see the assigned digit is 5, so the multiplier is 10 to the power 5. And the fourth color is your gold, that gives you the tolerance or the error, that is plus minus 5%. Unit is your ohm. If fourth color is silver, then it is plus minus 10% ohm. If there are no color, then it is plus minus 20% ohm. So it is all about your color coding of resistors.